Chris, is this working? It's working. All right. Hey, Chris, how you doing? Okay, so I can show you how cross product of vectors in physics works. So first, I want to talk about determinants. So if I have a matrix 1, 4, 3, 7, and I want to take its determinant, I will do a top left, bottom right product, 7, minus bottom left, top right product, 12, equals -5. So that's how you do a determinant of a 2 by 2. I'm going to do that again. The determinant of 4, -6, 3, 1 will be 4 minus a -18 is 22. So you can practice doing 2 by 2 determinants. So the next one is, let's do a 3 by 3 determinant. Well, the determinant of 4, 1, 3, 2, 5, 7, 3, 8, 6 will be. Now what you do is you go along the top row and you list them, the first number minus the second number plus the third number. So it's going to be 4 minus 1, there's some parentheses there, and plus 3. Now if I had a 7 by 7 matrix, I'd go the first guy minus the second guy plus the third guy minus the fourth guy plus the fifth guy. You go plus minus plus minus plus minus until you run out of stuff. So on a 3 by 3, it's the 4, then minus the 1 plus the 3. Now, after the 4, we're going to take the determinant of the 2 by 2 matrix whose numbers are not in 4s, column or row. So it's these 4 numbers here. We're going to take the determinant of that, which is 30 minus 42. Then for the 1, it'll be these 4 numbers. We're going to take the determinant of the 2 by 2 matrix whose numbers are not in this guy's column or row. So that's these guys. So 12 minus 21. And then this 3 will be the times the determinant of this, which is 16 minus 15. So that gives us 4 times -12 minus 1 times -9 plus 3 times 1, which is -48 plus 9. I think that's a plus 3 is -48 plus 12 is -36. Now on a TI-83, you would just do a, you can go into a matrix and fill this in and then do determinant matrix. You should get -36 when you do that. Alrighty, so I could do that with any size matrix as long as it's square. Now as far as vector cross product goes, let's take vector u. Vector u equals 3i hat plus 4j hat plus 5k hat. And vector v equals 1i hat minus 3j hat plus k hat. So the other way of writing vector u would be in vector notation 3, 4, 5, or 1, -3, 1. So any way you want to write that is okay. But to do the matrix cross product, works better if it's in this form. So what I'm going to do is I'm going to take the determinant of the 3 by 3 matrix whose top row is I hat, j hat, k hat. The second row is vector u, 3, 4, 5. And the third row is vector v, 1, -3, 1. Now, that gives me this guy here, I hat, times some stuff, minus j hat, times some stuff, plus k hat, times some stuff. What's going to be that stuff? Did my camera make it all the way over? Looks like my camera didn't quite make it all the way over there, did it? Yeah, well, sorry, dude. Anyway, I'm going to have I times 4 minus a -15, which is 4 plus 15, I'm going to have minus j hat times 3 minus 5. I'm going to have k hat times negative 9 minus 4. And that might have gone off the camera there, but what we've got is 19 I hat plus 2 j hat minus 13 k hat. So, when you cross product two vectors, you get a vector that is perpendicular to it. Now there are two directions that can go, the right way or the wrong way. So if you put vector u here and vector v, you will get u cross v. If you put vector v here and vector u there, you'll get v cross u. And of course we use the right-hand thumb screw rule. Vector u cross vector v gives us a perpendicular to those vectors, u cross v. Not this one, but this one. So we can draw a picture of what's going on. I'm going to try to draw. I got to check my camera and see if I'm in the right field here. I can go all the way over to, looks like I can go over, oh, okay. So here is a 3 coordinate axis. X comes out of the board, Y goes to the right, and Z goes up. So vector u is 3, 4, 5. So I'm going to go plus 3 on the x, plus 4 on the y, and that gives me the floor of a room. Then up 5 on the z. So I get this box that looks like this. And our vector goes x, y, z. So it starts at the origin and goes just like that, coming out of the chalkboard 3-dimensionally. It's kind of hard to draw on a chalkboard. Vector v goes out 1 on the x, the other way on the y, and then up 1 on the z. So 1, 3, 1, it comes over like that. Now, I claim that 19 to negative 13 is perpendicular to both of those. 19 to negative 13 is this vector right there. I claim that that is a right angle, and that at a funny viewpoint here, this is a right angle on that guy. Unless I made an arithmetic mistake, which is always the case, possible. But that is how we do cross products of vectors. Now to make sure that you're at least probably right, two vectors that are perpendicular dot to 0. So since this vector should be perpendicular to this one, they should dot product to 0. And since this vector is perpendicular to this one, it should dot product to 0. So let's find out. I'm going to call a new vector, vector d. So vector u dot vector d is the first components multiplied together, that's 57. And the second components multiplied together, that's 8. And the third components multiplied together, that's negative 65. And 65 minus 65 is 0. So that's probably a good sign. Vector v dotted with vector d is 1 times 19 minus 3 times 2. And 1 times negative 13 is 19 minus 19 is 0. So they are dotting together to give us 0. And so we're assuming that we went the right way. So let's go ahead and check that. This was vector u. That was vector v. Well, my hand ain't working out, but you get the point. It's gotta be that guy right there. Cross products of vectors. Let me know if that helped you out, dude. Thank you, Chris.